Hi everyone. We will talk about, previously we have talked about congruences on integers. Now we will talk about more on congruences and then some important theorems and results. So in this chapter, we are going to see some further results about congruences of integers. Most of these are to do with working out the congruence of large powers of an integer modulo some given number m. I showed you some ways of tackling this kind of equation question in the last chapter. Like you can see example 13.2 and 13.3. The first result of this chapter is Fermat's little theorem. It's a general fact that makes powers rather easy to calculate when m is a prime number. So the rest of the chapter consists mainly of the applications of this theorem to solving some special types of congruence equations, modulo a prime number or a product of two primes, and also to the problem of finding large prime numbers using a computer. So we will make heavy use of all this material in the next chapter on secret codes. Okay, perfect. So let's state the Fermat's little theorem. The topic is Fermat's little theorem. Okay. This very nifty result was first founded by French mathematician Fermat around 1600. So French Fermat in 1640. It's called Fermat's little theorem to distinguish it from the rather famous Fermat's last theorem. So there is Fermat little theorem and there is the Fermat last theorem. So this one is, so just to make it a different one, that's why it's written as Fermat's little theorem. Okay. Now, which is somewhat harder to prove. The Fermat's last theorem. Okay. Although, why the adjective little was chosen rather than large or medium sized or nifty is not clear to us. Okay. Anyway, let's state the theorem. We say let P be a prime number and A be an integer. That is not divisible by P. Then we say A power P minus 1 is congruent to 1 mod P. You can always give these brackets or like just not give them. So let's not stating them before. So let's not state. Okay. This is the Fermat's little theorem. So we have a prime number p, and we say that a be an integer that is not divisible by p. Then we can say that the p power minus 1 power of a is congruent to 1 mod p. Let's define it with more examples. So, for example, let's say we have p is 17. Applying the theorem with p is equals to 17 tell us that two power 16 is 1 mod 17. Isn't this interesting? Again, you can say 93 power 16 is congruent to 1 mod 17. And even 7 to 3 0 7 8 9 2 power 16 is congruent to 1 mod 17. What you need to do? You just need to make sure that p does not divide a, or like a is not divisible by p. And then you can use the Fermat's electrical theorem to express something very, very interesting. So this makes congruences of powers modulo 17 fairly painless to calculate. For instance, let's work out let's work out 3 power 972 modulo 17. Well, we know that 3 power 16 is congruent to 1 mod 17 by the theorem. Now, dividing 16 into 972, we get what? Or you can say writing 972 in terms of 16, we get 972 can be expressed as 16 times 60 plus 12. So we can write 3 power 972 equals to 3 power 16 power 60 into 3 power 12. Okay. Now, this means you can further express it in the congruences as 1 power 60 into 3 power 12 modulo 17, because 3 power 16 is congruent to 1 mod 17. So you just have to write 1 power 16 into this. So we only need to work out now 3 power 12 modulo 17. Now this is easily done using the method of successive squares explained in 13.3. So we can let's write it that. Now we only need to work out 3 power 12 modulo 17 and by example 13.3 we get 3 square is I'm going to 9 mod 17. So 3 power 4 is congruent to 9 square mod 17. Nine square, and then this can even further be written as 9 square is congruent to 13 mod 17. So 3 power 8 is congruent to 13 square, which is congruent to minus 4 square, which is congruent to 16 mod 17. Hence, we can write 3 power 972 is congruent to 3 power 12, which is congruent to 3 power 4 into 3 power 8, which is congruent to 13 into 16, which is congruent to 4 mod 17. So we can say that this is congruent to this. So with the help of this theorem, we can solve problems like this. So from here, we end up here. Okay? Now let's prove this theorem. Fermat's little theorem. Proof. For an integer x, for an integer x, write x mod p to denote the integer k between 0 and p minus 1, such that x is congruent to k mod p. So, for example, (17) mod 7 is nothing but 3. So we will write this to denote this k, is we will write this to denote 3. Okay, perfect. Because if you divide 17 by 7, you will get the remainder 3. So this is how we can write it. Also, for integers, x1 to xk, we write x1 up to xk mod p is an abbreviation for the list x1 mod p up to xk mod P. So for example, the list 1732, comma -1 mod 7 is 346. Okay. So to write these all like big expressions, we will only write this term. Okay, perfect. Now let A comma P be A's in the theorem. Multiply each side of the numbers numbers 1, 2, 3 to P minus 1 by A and take congruences modulo P to get the list. List A, 2A, 3A, P minus 1A, mod P. Well, let's call this 14.1. Now, to justify this, what we are doing, for example, or specify this, if P is 7 and 3, A is 3, this list is 3, 6, 2, 5, 1, 4. Just try to compute it, and then you'll find these are the numbers. Okay. Now we claim that now we claim that the list (14.1) consists of the numbers numbers 1, 2, 3 to P minus 1 in some order. To see this, note first that since P does not divide A, none of the numbers in the list is 0. Okay. Next, suppose two of the numbers in the list are equal. Okay. Okay. We can say that x a mod p is y a mod p, right? Where one is less than or equal to x, comma y, and they are less than or equal to p minus 1. Okay. Now saying that x a mod p is same as y a mod p is the same as saying that x a is equal to y a mod p, not equal to but congruent. Now, by proposition 13.52, this implies that x is congruent to y mod p, because a is both sides. So you can do that. And since x and y are between 1 and p minus 1, and since x and y are between 1 and p minus 1, this means that x is y. This shows that the numbers listed in 14.1 are all different. Okay. Is there are p minus 1 of them, and none of them is 0. They must be numbers 1, 2, 3 to p minus 1. in the same order, in some order. Okay. Now let's multiply together all the numbers in the list. Let's multiply together (14.1). The result is a power p minus 1 into p minus 1 factorial mod p. Since the numbers in the list are just in some order, this product is also equal to p minus 1 factorial mod p. Okay, so in other words, a power p minus 1 into p minus 1 factorial mod p is equal to p minus 1 factorial mod p. Which means that a power p minus 1 dot p minus 1 factorial is congruent to p minus 1 factorial p. Now p does not divide p minus 1 factorial. Since none of the factors is divisible by p, which means since none of the factors which are p minus 1, p minus 2, 3, 2 is divisible by p. Hence, proposition 13.52 allows us cancel p minus 1 factorial in the above congruence. Equation to deduce that a power p minus 1 is congruent to 1 mod p, and this completes the proof. So this is how we prove the Fermat's little theorem. Okay, so you can go through it by pausing the video and then reading it again and again. And if you have any questions, you can post into the comments and I can answer that. Now notice that Fermat's little theorem implies that if p is prime, then a power p is a mod p for all integers a. So let's talk about some consequences. So notice that Fermat's little theorem implies that if p is prime, then a power p is congruent to a mod p for all a as an integers, regardless of whether a is divisible by p or not. Since if p divides a, then a power p is congruent to a, which is congruent to 0 mod p. Okay. For a different proof of Fermat's little theorem, see exercise 9 at the end of chapter 16. So we'll try that and we'll see that. So it is possible to use Fermat's little theorem to show that a number n is not a prime without actually finding any factors of n. For example, so this is a very nice consequence. It is possible to show, it's possible to use Fermat's little theorem to show that a number n is not a prime without actually finding any factors of n. For example, suppose we are trying to test whether the number 93 is prime. Check 943 is prime. One test is to raise some number, say 2 to the power of 942, and see whether the answer is congruent to 1 modulo 943. If it's not, then 943 is not a prime by Fermat's little theorem. In fact, using the method of successive squares, we can calculate that. So let's try that. So one test is to raise some number, say 2 to the power 942 and see whether the answer is congruent to 1 modulo 943. If it's not, then 943 is not a prime. By Fermat's little theorem, because if a power p minus 1 is congruent to 1 mod p, then p is prime. That is the theorem. So we can see that 2 power 942 is congruent to 496 mod 943, showing that indeed 943 is not a prime. So, of course, for such smaller number as 943, it would be much easier, much quicker to test it for primality by simply looking for prime factors less than under root 943. However, for really large numbers, the above test can be rather effective. Let's call it the Fermat test. This test is Fermat's test. And this test is by no means always successful in detecting the non-primality of a number. For example, you will find that 2 power 340 is congruent to 1 mod 341, which gives you no information about whether or not 341 is prime. In fact, it is not prime, since 341 is 11 times 31. This test is Fermat's test, is known as Fermat's test. The Fermat test is by no means always successful in detecting the non-primality number. For example, 2 power 340 is congruent to 1 mod 341, but 341 is no prime. Because 341 is 11 times 31. So indeed, there are some numbers n that are not prime yet satisfy the Fermat's literal theorem for an integer, for all integers a co-prime to n. And for these numbers, the Fermat's test will never detect the non-primality. The smallest such number is 561. Okay. So you can say, indeed, there are some numbers n that are not prime, yet satisfy a power n minus 1 is congruent to 1 mod n for all integers a co-prime to n, and for these numbers the Fermat's test will never detect their non-primality. Okay. We shall see in the next chapter that it is very important to be able to find very large primes using computers. So finding good primality test is vital. There are some clever refinements of the Fermat test. It worked well in practice, and I'll discuss this in this chapter. Now, before moving on to the next section, we note that the following result, which is an easy consequence of Fermat-Little theorem. So let's note that. We call it proposition 14.1. Say let P, Q be distant prime numbers. Let A be an integer that is not divisible by P or by Q. Then you can write A power P minus 1 into Q minus 1 is also congruent to 1 mod PQ. This is very interesting result, and we will prove this. So by Fermat's little theorem, we know that A power P minus 1 is congruent to 1 mod P. Now taking Q minus 1th powers both sides. By proposition 13.4, we are doing that by proposition 13.4. It follows that A power P minus 1 Q minus 1 is congruent to 1 mod P. Okay. Similarly, A power Q minus 1 is congruent to 1 mod Q, and hence also A power P minus 1 Q minus 1 is congruent to 1 mod Q. Therefore, both P and Q divide A power P minus 1 Q minus 1 minus 1. So PQ divides this number. since P and Q both appear in its prime factorization. So in other words, A power P minus Q into Q minus P minus 1 into Q minus 1 is congruent to 1 mod PQ as required. Perfect. We will end this part of this chapter here. We'll continue in the next one.